Hello, I'm Chris Porter, and I'm presenting CASE, a compiler-assisted scheduling framework for multi-GPU systems. My co-authors are Chao Chin and Santosh Pandey. GPUs are a fundamental component for high-performance computing. Multiple GPUs per node are now the common case. For example, the most recent HPC system, Frontier, will house one AMD EPYC CPU with every 4 Instinct 250X GPUs. The previous generation supercomputer, Summit, boasted similar hardware. It had 2 IBM Power 9 CPUs to accompany every 6 NVIDIA Volta GPUs. Core and memory capacities haven't stalled either. Very recently, Volta-era GPUs had about 32 gigabytes of RAM, but these are being surpassed by more massive GPUs with memories in the vicinity of 128 gigabytes. That's great, right? More, better? Well, unfortunately, despite this growth, GPUs are still relatively underutilized and expensive. They achieve roughly 30% utilization for many scientific applications, and in terms of cost, they are typically 2x to 5x as expensive as comparable high-end CPUs like Intel Xeons. So GPU VM instances in the cloud might be convenient, but they're also expensive, costing nearly 10x as much as regular VMs. Because of this, there's still a need today to improve GPU utilization. And a key reason why this hasn't been so easily solved is because scheduling multiple CUDA tasks on one device is unsafe because it can lead to out-of-memory errors on the GPU device. We propose a framework that can help with this. We built a compiler-assisted scheduling framework for multi-GPU systems. We target the single-node multi-GPU case. Our goal is to share GPU devices among independent, uncooperative applications, thereby improving the system utilization with negligible performance interference per workload. We will also show how this improves throughput for a batch of GPU tasks by up to 2 to 3x, and we will use the compiler to generate resource requirements at runtime that lead to a simple scheduler. All of this is fully automated. Our talk has 3 main parts. We will briefly touch on state-of-the-art work, then we'll share details of our framework case, then we'll close with a discussion about our results. First, prior art. There's a significant amount of research that has gone into various aspects of GPU sharing, utilization, and performance. Slurm, FLEP, and NVIDIA MPS are 3 very different types of solutions, but which help illustrate a tradition of more effective multiprocessing with GPUs. So Slurm is a job queuing tool. It's concerned with resource reservation, and it's not GPU specific, but it does support systems with multiple GPUs per node, and it enables users on shared systems to reserve a subset of available GPUs, and thus, in effect, share them. It's conservative, ensuring that different users are guaranteed the GPUs requested for the duration of a job. FLEP solves a different problem, but it's still relevant to us because it's concerned with how to share GPUs. It's a kernel slicing technique, which allows for more effective preemption. Subkernels can be preempted and reassigned to higher priority ones. It doesn't solve the problem of how to co-execute multiple GPU jobs on one device. For that, users can take advantage of NVIDIA's multi-process service. MPS enables simultaneous execution of multiple kernels. The assumption, though, is that different processes' kernels are cooperative, like with MPI tasks. The developer is completely responsible for managing the memory and not overloading it, because MPS makes no guarantees on this. And if, for whatever reason, the processes are independent and do not know about each other's resource needs, out-of-memory errors are completely uncontrolled and possible. This is not a complete list, of course, of related work, but it's somewhat representative. Today, you can get basic conservative sharing with a system like Slurm, or you can go down these paths of preemption and more CPU-like control over your kernel's GPU residency, or you can even get full co-execution of your processes on a GPU. But there's little to no work on safe, efficient sharing of independent, uncooperative processes for this multi-GPU single-node case. This brings us to a recent research prototype, SchEduling. It attempts to solve at least the out-of-memory problem by having applications share their resource needs before launching on the GPU. This requires programmers to manually rewrite parts of their code to estimate memory usage and to insert API calls for this. Though this technique can be applied to multiple GPUs, it's not a main focus of their work. Thus, if multiple applications are written to all use device 0, for example, there's no technique for moving certain kernels to device 1. All of them would end up sharing device 0, albeit in a memory-safe manner. This figure 3 is drawn from the creator's paper and shows how it works. you'll notice multiple CUDA applications all link against the CUDA library and the SchEduling library. They communicate over shared memory with one another, and their shared resource needs allow them to cooperate, not overrun the GPU's memory. Though SchEduling is an advancement over just using NVIDIA MPS, there are still shortcomings, such as the lack of automated support for identifying the resource needs, a deliberate technique for leveraging multiple GPUs on a single node, which is an architectural detail which is now the norm, or a scheduling technique to handle this multi-GPU case. So CASE is our compiler-assisted scheduling technique that will address these concerns. This diagram is a high-level view of how our framework and how it's positioned in a basic hardware-software stack. We can see applications sit at the top of the stack and GPUs lie at the bottom. The interface to the GPUs is the CUDA runtime, but somewhere in the middle between the applications and the CUDA runtime is our framework. It consists of an offline component, namely the compiler pass, but its lazy runtime and the scheduler interact during the application's execution to help direct them to a proper GPU. Note that our framework integrates with the CUDA runtime and depends on it for certain functionality, such as being able to place more than one application on a GPU. Here's a simple motivating example of how our CASE framework operates. Consider 2 GPUs and 2 applications. Also, for the sake of this example, we'll assume both applications have 2 kernels that they want to schedule simultaneously. So application 1's kernels both fit on the devices. That is, we could assign K1 to device 0 and K2 to device 1. Similarly, if we take application 2 in isolation, it can assign K1 to device 0 and K2 to device 1. The problem, however, is that if these applications run together, there's not enough memory on device 1 to support K2 from both applications. Each requires 9 gigabytes, and the device has only 16 gigabytes. If, however, application 2 assigns K2 to device 0 and K1 to device 1, then all 4 kernels can fit on the 2 devices. Though this example may seem relatively simple, the challenge is somewhat technical. The key is to get the resource requirements for each kernel. This includes the computing resources, such as the streaming multiprocessors, which can help a scheduling system identify performance interference, and it includes the memory footprints, which are critical to avoid out-of-memory errors and crashes. CASE's approach is a mix of static program analysis and dynamic runtime binding. We start with the simpler case, constructing GPU tasks statically. We define a GPU task as a group of GPU operations for a kernel launch. Thus, a GPU task includes memory allocation and initialization, the kernel launch itself, and any saving of the results. Also, kernel launches that share any memory objects are merged into the same task. Here is an example to explain what we mean. This simple program adds 2 vectors on the GPU. The main function begins at line 8. It invokes vecadd at line 29. The kernel code itself is highlighted in dull pink. All of the kernel-related operations are highlighted in bright blue. Our static instrumentation has already been added in this example, and it's colored in dark blue. Do you see lines 17 and 37? Task begin and task end are our instrumented functions. Our framework automatically instruments those lines with the resource requirements of the GPU task. The question is, how? Well, our static analysis starts by identifying the kernel launches. In this case, there's only one, which is at line 29. Notice how the kernel launch specifies its compute requirements, namely the number of blocks and threads per block. These are colored in yellow. And it specifies the objects to be worked on, which are colored in red and which are directly associated with CUDA-malloc calls. In other words, the parameters to the kernel launch tell us the compute and memory requirements of the kernel, and we just need to ensure that we instrument the code with said information just before the task begins. We rely on def use analysis to identify the definition points and participating variables of the GPU task. I'll show how we can use this resource information shortly, but before that, let me show you how we have to do this for a slightly more difficult example. Static analysis may not always work, so we have to delay certain CUDA operations until runtime. Here we have a similar code example. But the CUDA-malloc calls are inside of an init function starting at line 6. This kind of code pattern is common, and in fact, it makes static analysis more difficult because our go-to technique, namely def use analysis, does not play nicely in interprocedural cases. So what we do is we replace CUDA malloc with our own lazy malloc call. At runtime, lazy malloc will assign a unique ID to A rather than allocate actual memory on the device, and will enqueue the kind of operation we want, in this case, a malloc of size n. We do this for other calls, including calls like CUDA memcopy, and each object will get its own ID. Just before the actual kernel call happens, we'll issue a task begin with materialization, which will perform the actual CUDA operations that we enqueued. The takeaway here is that the compiler replaces and instruments code automatically so that the compute and memory requirements of GPU tasks are always made known. But I didn't tell you how we actually use this information. So this sequence diagram shows how the resource needs of a GPU task are passed by task begin to a runtime scheduler. The function call sends a probe with the resource needs. The scheduler uses that to determine an available device, and then it returns a device ID for the GPU task. The process itself uses CUDA set device to select the device. Now, how exactly did the case scheduler decide on the device for a given task? Well, we looked at two different scheduler algorithms. The first is hardware emulation. The idea is to only add a task to a GPU if the GPU has compute and memory available. This is effectively how the hardware operates. So we emulate this with the scheduler. We have to track the number of active threads on each GPU. To do this, we schedule a task on a GPU. To do this, when we schedule a task on a GPU, we assign a task's threads to the thread blocks on the GPU's streaming multiprocessor. Our scheduler doesn't technically have control over this assignment, but we can still track the totals. Of course, we also ensure the GPU has memory available. We never assign a task to a GPU if compute or memory is already saturated. Our second algorithm is simpler. We looked at a slightly easier way to do this. So the basic idea is the following. For some incoming task, find the GPU with 1, memory available for it, and 2, the least number of active warps. Note that memory is still a hard requirement. A GPU must have memory available for the task, or we cannot schedule the task on it. Compute, however, has been relaxed to a soft requirement. Once we know which GPUs have enough memory available for a task, we just want the least loaded GPU. Our pseudocode for this second scheduling algorithm is shown on the right. We take in some task and a list of GPUs. We initialize the targeted GPU to nil and the minimum warps over all GPUs to infinity. Then we check all GPUs. First, we see if the task can fit on a GPU, and if it can, we check if that GPU is least loaded. If so, we update the targeted GPU for the task. At the end, we return the targeted GPU so that the process can call CUDA set device with it. Here's an example of how this second scheduling algorithm would place a kernel on a set of GPUs. Here we have 4 GPUs with different amounts of free memory and end-use warps. Our scheduler wants to place kernel K0 on a GPU. Our algorithm proceeds as follows. It first checks the GPUs to see which of them have enough free memory to hold the kernel. In this case, we can see that K0 has a memory requirement of 6 gigabytes. G1 has 10 free gigabytes and G2 has 8 free gigabytes. So both of these are candidates. Then our algorithm checks the in-use warps for those candidates. This is a soft requirement, so both GPUs are candidates. G1 has 3 million in-use warps and G2 has 2 million in-use warps. Again, we want the GPU with the least load, which in this case is G2. Thus, we select G2 as the target GPU for K0, and we update G2's free memory and in-use warps based on K0's values. Let's move into the evaluation. We use 2 different systems, one with 2 Pascal GPUs and one with 4 Volta GPUs. Both the P100 and V100 GPUs have 16 gigabytes of RAM. The V100 is newer, however, and has more features and more CUDA cores as well. The CPUs used for both systems are comparable, though the 4 GPU system benefits from more system memory. By using these 2 different systems and both a 2 and 4 GPU node, we were able to test that that case continues to show benefits on larger systems and for the newer architectures. We tested with 2 different kinds of workloads, Rodinia, which is a traditional benchmark suite for parallel computing, and Darknet, which is a neural network framework that we can run neural network loads on. We created mixed workloads for Rodinia based on 7 benchmarks in the suite that have realistically large kernels. We randomly selected jobs, either in sets of 16 or 32, and with varying ratios of large to small jobs. Large for us is considered 4 to about 12 gigabytes. Small is memory footprints of 1 to 4 gigabytes for a kernel. And for darknet, all of our workloads are 8 jobs of a homogeneous type, namely neural network training, neural network prediction, real-time object detection, or text generation. We compared against 3 other schedulers. Single assignment is similar to job queuing systems like Slurm. It can only assign 1 kernel at a time to a GPU. Core to GPU is a generalization of this. It can assign multiple jobs to each GPU based on a limited predefined number of cores or workers per GPU. This is unsafe because there's no guarantee that the memory can hold the jobs. And we compared against the previously mentioned state-of-the-art research scheduler called SchEduling. It can support memory safety within 1 GPU, but it requires programmers to modify their code to supply resource needs via an API. So briefly, we'll use an example to illustrate how each of these schedulers works, starting with the single assignment scheduler. Here we have 4 kernels and 2 GPUs at time 0. And at some time t1, the single assignment scheduler will place K0 and K1 on the 2 GPUs. And at time t2, we can see that K1 is completed, so the single assignment scheduler has placed K2 on the newly available GPU. So relatively straightforward. Each GPU is kept active with 1 kernel at a time. The core to GPU scheduler will have some number of CPU cores producing work for each GPU. Here we're showing 8 kernels and 2 GPUs. And let's assume also that 2 CPU processes will be responsible for producing work for each of the GPUs. Thus, at time t1, we can expect to have K0 and K1 on one of the GPUs, and K2 and K3 on the other. Similarly, at time t2, we can see that K0 has completed, so K4 has been added to the first GPU. As we can see, this resembles the single assignment scheduler, except that we are allowed to have multiple kernels on each device. This is unsafe, and it does not consider load on the GPUs. Lastly, we illustrate our third baseline, namely SchEduling. Here we have 4 kernels and 1 GPU. We also have more details now. We can see that K0 and 1 have 8 gigabyte footprints, and K2 and 3 have 10 gigabyte footprints. And the GPU has 16 gigabytes of memory. Thus, at time t1, SchEduling would be able to place K0 and K1 onto the GPU, but at time t2, after K0 has completed, SchEduling would have to wait because K1 and K2 cannot both fit at the same time. Now, to summarize the results, CASE improves GPU utilization by up to 3.36x. On average, its throughput improvement for Rodinia and darknet workloads are about 2x. The job turnaround time, which is measured as the time between the start of the batch and the completion of a job, improves by up to 4.9x, and the individual kernel performance degradation, which can happen when simultaneously executing kernels compete for resources on a GPU, was at most 2.5%. We'll start with a comparison of the 2 schedulers shown earlier, the hardware emulation technique versus a simplified version. Well, here we have the results on the 4X V100 system. The x-axis shows 8 workloads, which are 16 and 32 job random mixes of the Rodinia benchmarks. And the y-axis shows the normalized throughput of the simplified approach over the hardware emulated approach. What we observed is that, in general, holding back jobs when GPU compute is saturated does not yield any significant benefit. Rather, it's better to add the jobs, given that there's memory available, and allow the hardware to handle the co-located jobs. The gains are modest, but significant enough to prefer the simplified approach. As we can see here, the average improvement hovers around 1.25x for these workloads. Now, this graph shows our throughput results on the Volta system on the Rodinia benchmarks. All the rest of the results were using the simplified scheduler here. Now, the x-axis shows, again, the 8 workloads, which are the 16 and 32 job random mixes of the Rodinia benchmarks. And the y-axis shows the normalized throughput over single assignment. In all cases, except workload 1, CASE outperformed both the single assignment and core to GPU schedulers. In workload 1, the CG scheduler happens to schedule more kernels on a GPU without causing a crash. And so it executes slightly faster. Now, the average improvement over single assignment is roughly 2x for case, and case achieved up to 2.5x improvement over the single assignment on workload 5. Now, this graph shows the Volta system's throughput improvement on darknet. In this graph, the results are normalized against SchEDuling. The x-axis shows the neural network task, the 8-job homogeneous mixes, and the y-axis shows the normalized throughput. Case achieved an average of roughly 2x over SchEDuling. The peak is a little over 3x for the text generation task. In the case of real-time object detection, the tasks are significantly smaller and shorter than the others because the responses from the network must be fast by design. Thus, for these, there was little interference among the jobs, regardless of placement, and both schedulers performed similarly. In summary, we presented CASE, a fully automated GPU scheduling framework for uniformly and transparently managing GPU resources. It combines static analysis, a lazy runtime, and a scheduler. It guarantees memory-safe execution of uncooperative processes, and it shows strong performance improvements, 2.5x boost in throughput, over 3x in GPU utilization, and almost 5x in job turnaround time. Our artifact is available on Zenodo, and we also have follow-on work appearing in GPGPU 2022 that applies CASE to NVIDIA's new multi-instance GPU feature, and which shows similar improvements. Thank you for listening.